Hello, Scientific Applications and Research Associates here to discuss our low-altitude airspace monitoring technology using passive acoustics. This is a technology to provide due regard for the U.S. Navy and to help manage airspaces in IMCOM environments. It is based on our work around SBIR topic N151026. First, a little bit about Scientific Applications and Research Associates, or SARA. We were founded in 1989 as an advanced research corporation, a DARPA house, if you will. But now we're branching our extensive portfolio of technologies and IP into the product space. We currently have a technical staff of over 200 folks, and our main locations are in Cypress, California, and Colorado Springs, Colorado. We have world-class expertise in aeroacoustics, aircraft electromagnetic pulse, or EMP, and radio frequency direction finding. Our core products right now are aircraft electromagnetic pulse hardening. We do many of the aircraft around the United States, facilities for EMP hardening, low-cost radio frequency direction finders. Currently, we are the prime of an Air Force Vanguard program to develop cooperative munitions using RF seekers, and a helicopter acoustic gunshot detection system, which we have in production and is designed and manufactured by SARA but integrated through Northrop Grumman. And of course, today's subject, detect and avoid for our small UAS. And of course, as well as special projects. The need for due regard systems in airspace management for small UAS is not only the topic of this SBIR, but is the subject of much investment at SARA and through several commercial and military partners that are teaming with SARA to address this need. Our first need is for an collision avoidance system, or a detect and avoid system, that does not rely on, but might be used synergistically with, transponders such as ADS-B, so that small UAS can detect other aircraft and maintain a safe distance from them. With few exceptions, Navy manned and unmanned aircraft don't operate in the same airspace at the same time, and this is a restriction or a limitation on operations. We seek to satisfy a need for organic capability to detect manned and unmanned aircraft to ensure safe separation of aircraft within an airspace. They may be more tightly coordinated in operations, and so that operations may be more efficient, particularly around ships. With the proliferation of UAS and the coming of fully autonomous UAS, the push for autonomy and lower staffing in ships, coordination of the airspace around ships becomes more of a challenge and requires more advanced tools to help coordinate that airspace and keep it safe around ships. The opportunity is the ability to increase the tempo of air operations around ships. So in this way, the Navy can be more effective overall. In transit, UAVs must comply with due regard. They must pay due regard to the rules of civil aviation and remain well clear from civil aircraft and other friendly military aircraft. They may even coordinate operations with manned aircraft to form a more collaborative, effective force. And all this might need to be done in INCON situations where Aegis radar or other traditional surveillance methodologies are not available. In CONUS, UAVs may transit from one location to another within the national airspace, and they must pay attention to the rules of the FAA and remain well clear from civil aviation. Developing a due regard system or a detect and avoid system for small UAVs is an immense challenge. You could never fit an Aegis radar on an SUAS. Even 1/1000th of such a radar would never fit on one of these UAVs. And if you were radiating, you would just be telling the enemy where you're coming from. You also face collision from all directions, 360 degrees, because UAVs are slower in general than the other aircraft that might be around them that they might encounter. So you need a 360-degree coverage from the UAS itself. These systems require very low swap. That's why we have developed an acoustic-based detect and avoid system that detects aircraft and determines how to avoid them using acoustic surveillance. If you pay attention to how you detect aircraft, you'll find almost always that you hear them first and then try to find them with your eyes. It's very natural. We haven't enhanced the human hearing system and put it on a UAV. Our microphone array can detect and direct and locate aircraft much better than the human ear can. It can hear down to frequencies that the human ear just can't hear, frequencies that are critical for detecting aircraft in the airspace. We have developed technologies to address the two forms of noise faced. The first of these is flow noise. Try driving down the road, rolling your window down, putting your head out, and trying to hear the noises around you. The flow noise is the turbulence around your ear. We have developed enhanced technologies that eliminate this flow noise. We've also developed technologies, algorithm technologies, that take out the engine and the propeller noise of an aircraft so that when you're out flying around, it is the perfect place, the perfect listening environment. You can hear other aircraft from very far away, all at very low size, weight, and power. Our weight is 500 grams and decreasing with each development cycle. Our power is 5 watts and similarly decreasing with each development cycle. We do all of our processing on board, and we can interface with the autopilot and also the ground controller for pilot in the loop, pilot on the loop, or fully autonomous ConOps. We've integrated on many UAS. Shown here is an integration on the RQ-20 Puma, which handles its unique recovery method, which is crash landing. Our microphones are designed to come right off upon crash landing. And as the wing comes off, our wiring harness is designed to separate as well. And we have designed microphone arrays for many different recovery methods on many different UAS. We've extended our acoustic detect and avoid technology to a ground-based system that we call the Terrestrial Acoustic Sensor Array System, or TASA. These sensors provide passive, IMCOM-compatible airspace surveillance around the sensors themselves and can be networked to multiple sensors through LTE networks or other radio networks to provide a whole surveillance network. Surveilling an airspace regardless of line of sight, day-night conditions, or cloud cover. And again, completely compatible with INCOM operations, completely passive. We've been exploring ConOps for ship operations using these sensor arrays. Several such ConOps include terminal control of the airspace and also terminal phases of recovery of UAS. We've evaluated them in Navy-sponsored ship tests starting back in September 2020. We again are testing again with NavAir in May 2020, and with the Fourth Fleet via fleet experiment in July 2021. We already have commercial sales of these systems, and we've been operating networks of these systems with the FAA, one in Blacksburg, Virginia, and another surveillance network in North Dakota. They've evaluated these systems for over 90,000 hours since the fall timeframe, through the different weather conditions and through different aircraft encounters, in order to coordinate and maintain safe airspace for UAV operations. With our commercial partners, we have achieved the world's first approval for fully autonomous UAV operations using TASA. And we continue to mature and develop this technology both in its military applications and in its commercial applications. We have developed our acoustic airborne system based on the SBIR, and derivative from it, our ground-based system, TASA. We call our system for the Navy the Passive Acoustic Non-Cooperative Aircraft Motion Analyzer, or PANAMA. We have modified that system slightly, mostly in software, to meet the DA performance standards of the ASTM Standards Committee. We call that system Passive Acoustic Non-Cooperative Collision Avoidance System, or PANCAS. We have integrated our PANCAS onto the RQ-20 Puma, which we are transitioning through NOAA and the U.S. Coast Guard. We recently signed a CRADA with the U.S. Coast Guard for continued testing, and we completed a series of testing with the U.S. Coast Guard through the summer of last year. We've integrated with NASA PANCAS on the HQ-90, the L3 HQ-90, for their Resilient Autonomy program. They're continuing to integrate that system, use as a test bed for fully autonomous UAS, and for NASA to continue to develop the rules and regulations and understand the capabilities of fully autonomous UAS in the national airspace. PANCAS was independently evaluated by the Air Force Test Pilot School, where it received a satisfactory rating out of possible ratings of fail, marginal, and satisfactory in achieving its performance. And our TASA systems, as I mentioned, we are currently selling to commercial partners, and we are evaluating them for shipboard operations. The benefits of both Panama, PANCAS, and TASA to the Navy are multiple. The first is the ability to operate UAS and manned aircraft in the same airspace with the potential to increase the tempo of operations and allow more autonomy and perhaps less staffing. There's also the path to FAA authorization to operate UAS in the national airspace, which would benefit the Navy in flying UAS in the national airspace and relocating them from one area of operations or one base to another. Providing a path to due regard so that the Navy can make sure that it satisfies the rules of civil aviation in the airspace that it flies through, also allowing for more efficient operations, less planning, and more capability. Of course, managing both manned and unmanned traffic, especially in coordination together, cooperative UAV, manned aircraft in NCOM situations is an opportunity, a possibility that is provided by PANCAS. Extending the allowable range, that is the flight distance of UAS, even in non-NCOM environments, to beyond the range of radars or outside the line of sight of those radars is another benefit to the Navy. SARA is placing significant emphasis on transitioning these technologies to the fleet. We have integrated PANCAS on the RQ-20, the HQ-90, and are in works to integrate on several other platforms, including the RQ-21 and other UAS. We demonstrated PANCAS on the RQ-20 with the U.S. Coast Guard and NOAA, who are interested in transitioning it to their fleets. We have integrated PANCAS on the HQ-90 for NASA with ultimate transition path to Southcom. TASA has been demonstrated on a ship at NAVAIR in September 2020, and we are going to demonstrate it again in 1 month in May 2021. We have a transition path through NAVAIR PMA 263, which is our current, which is currently funds this opportunity, and we have a fleet experiment with the 4th Fleet in July 2021 with both Panama and TASA. There are many commercial transition opportunities, and we are already experiencing commercial sales. So we've already transitioned this technology to dual use. If you'd like to learn more, visit the SARA booth, or more importantly, visit our website at www.sara.com, which has a lot of information on these technologies. If you'd like to reach out to us, reach out to our mission director, Jesse Klang, at jklang@sara.com, 714-414-8127. Thank you very much.